Hello and welcome to Engineering Simple. In this video series, I'll be talking about line to ground faults applied to low voltage side of a transformer and calculating that line to ground fault, then calculating the current that a tertiary or stabilizing delta winding has to carry, and also calculating the current that the high voltage and low voltage windings will need to carry, for a line to ground fault applied to a low voltage side. And we'll use network sequences. So here are some objectives of these videos. So we'll learn how to apply symmetrical components. Symmetrical components are positive, negative, and zero sequence components. Then we'll learn how to calculate the equivalent system impedances, then how to establish network sequences. Then we'll learn how to calculate the line to ground fault on low voltage side of a transformer. Then learn how to calculate the current that at delta. So I call it tertiary, but really the proper name is stabilizing winding. But industry-wide, typically they call it tertiary, so that's why I call it tertiary. But what I'm really referring to is the stabilizing winding. Basically, it's a delta that's not connected to the load. It's there just to handle zero sequence currents and also suppress any third order harmonics. Then we'll learn how to calculate, based on this line to ground fault on low voltage side, calculate the current that will be seen by the high voltage windings, and also calculate that current. Then calculate the current that the low voltage windings will see. So obviously, you have the line to ground fault, which I will go through in this video. You have three-phase fault, you have line to line, line to line or line to ground faults, and the windings will have to be able to handle all these faults. But in this video, I'll just talk about line to ground fault. So let's assume we have a 345 kV to 138 kV system. Basically, just for simplicity, it's one transformer, and typically that's true for transmission, because these transformers they have a higher rating, 400 MVA and above probably. But let's assume we have an auto transformer. So you have an auto. So basically, here are the windings. So you have H1 terminal or bushing, H2, H3. So the neutral, HO, XO bushing, and it's grounded. HO, basically the high side neutral and the low side neutral are common, are one. Then since it's an auto transformer, so you bring one lead, and that's X1. So I would recommend watching some of the videos I made on auto transformer. So this is called the series winding because it's in series, and this winding here is called the common winding because it's common to the high voltage and low voltage. So as you can see in an auto transformer, as I stated, I would recommend watching those videos. You see the high voltage, basically it's from here all the way to the neutral point. The low voltage is just from here to the neutral. So the low voltage is the same as the common winding, but the high voltage is series plus common windings. Then you have X2 somewhere here. in X3. So H1, H2, H3, that's the high side. X1, X2, X3, that's the low side. And the auto transformer, the windings, the high voltage and low voltage windings are electrically and magnetically coupled. So there's an electrical or physical connection uh, between the high voltage and low voltage. So let's assume the high voltage, this transformer you have, they go to a transmission line, for instance, somewhere here. I'm just randomly drawing these. And since this one H1, I'm just call it phase A, phase B. So these are transmission lines basically. So they can be, who knows, 10 to 100 miles or more basically. So these are, just think they're transmission lines. And transmission lines basically, they have resistance plus reactance, so R plus JX. Then we'll do the same thing for low voltage windings. So the low voltage windings, so you have X1, let's call that lower case A phase, and X2, so that's phase B, that's C. So, and these are transmission lines too, they can be from 10 to 50 miles, or it just depends long. So basically from here they go to another substation probably. So these are 138 kV lines. So they go to another substation where you have another transformer. So it's 138 kV to either, it can be 69, it can be 34 kV, it can be 12 kV, 4 kV, so on and so forth. So this side here is 345 kV. And they can either go to a generation or go to another substation. So, but you can see then, so this is an auto transformer. So it's connected basically grounded Y. Then we have a delta, the stabilizing winding, or tertiary, as some might call it. So, and typically this here, just one corner is brought out of the tank. So if you assume this is the tank that these windings are located, so one corner will be brought out and grounded. The other corners of the delta, so basically this side here and this one, will be floating internally. They are not connected to anything. So this, if you want to write the vector, probably you would write grounded Y. So you have the N and probably A for auto. Or you can write ND. So grounded Y, D, and 2. So this would be D1, meaning the high voltage 345 kV leads the delta by 30 degrees. And I would recommend watching the videos on vector groups. But obviously this here probably would imply that they're electrically separated. Basically, it's like if you take just single phase, like two windings, you see you have the high voltage, you have the low voltage, and here's the core that are wound around the core. You can see there is no electrical or physical connection between the high voltage and low voltage. The opposite with the auto transformer. They are electrically and mechanically and magnetically connected. But you can see this three-phase drawing here is kind of messy. So when we are dealing with power system, we don't do three-phase. We just draw the one line. So in other words, this is much simpler and much easier to deal with. So you just kind of show that here's a transformer. So you have this side is Y, and basically you can just do this that way. It's an auto transformer. Sorry, this is the way it's here. Then you have the delta. You can just show that there is a delta, probably another winding here, something like that. But then, so we'll call this H kind of side or bus. This is the X bus. So basically this is 345 kV to 138 kV. And you have the H, and let's say the equivalent system, let's call this A, and let's call this B, because we don't want to draw the entire system. So like the equivalent source basically, and we know it's grounded. So you can do the same thing here. So you have, here's the transformer, and these basically you just use the equivalent system, because when you think about the power system is networked, there's a lot. It's not just two systems, it's so networked. But when we're doing studies, we don't need to know everything about the rest of the system. We can just use the equivalent system. So you see, this is a lot simpler than the three-phase. So this is typically what you would see when people are dealing with power systems. So I will stop here, and in the next video I'll draw the positive, negative, and zero sequence networks, and then I will apply a line to ground fault on the low voltage, and from there I will calculate the equivalent impedances and calculate the fault currents that the high voltage, low voltage, and the delta winding need to be sized for if a line to ground fault on the low voltage winding or the low voltage side occurs. So thank you and have a great day.